Hi all. Today we are going to discuss about the fundamentals of electrical engineering. Fundants are basic electrical terminologies, resistance, capacitor, inductor, Kirchhoff's laws, basic terminologies regarding magnetic circuits, Faraday's laws of electromagnetic induction, Lenz's law, electromagnetically induced EMF. Basic electrical terminologies. First one, electric current. The electric current is a flow of free electrons. That is the current I equal to charge divided by time. That is equal to Q by T. That is the unit is coulombs per second or ampere. Electric potential. The electric potential is the capacity of a charged body to do work. That is V equal to W by Q. Work done divided by charge. The unit is joules per coulomb or volt. Potential difference. The difference in electrical potential at any two given points is called the potential difference. Let VA and VB be the potentials of points A and B respectively with respect to the ground. Then VBA is the potential of point B with respect to point A. Then VBA will be equal to VB minus VA. Electric power. Electric power is the rate at which work is done in an electric circuit. That is power P equal to work done divided by time. That is equal to joules per second. That is equal to watt. There is another equation for electric power, P equal to IV. That is, I is the current and V is the voltage. Resistance. It is a property of a substance which opposes the flow of electric current. That is, R equal to rho L by A, where rho is the resistivity of the material, L is the length of the conductor, and A is the cross-sectional area. The unit of resistance is ohm. Different types of resistor is shown in the figure, and the electronic symbol for resistor is also given in the figure. Ohm's law. The Ohm's law states that at constant temperature, the voltage V is directly proportional to the current I, where the constant of proportionality is the resistance R. The Ohm's law triangle is shown in the figure. According to that, V equal to I into R. And also we will get another equations, I equal to V by R and R equal to V by I. Resistance in series and parallel. Let the resistances R1, R2, R3 be connected in series. Then the equivalent resistance R equivalent will be equal to R1 plus R2 plus R3 plus etc. Similarly, if the resistances are connected in parallel, R1, R2, R3, etc., then the equivalent resistance 1 by R equivalent will be equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. Capacitor. The capacitor stores energy in the form of an electric field. The unit of capacitance is farad, and the equation for the capacitance C equal to Q by V, and also Q equal to C into V and V equal to Q by C. The different types of capacitors are shown in the figure and also the electronic symbol. Inductor. Inductance is a property of a material by which it opposes any change in the current flowing through it. The unit of inductance is Henry, and the equation V equal to L di by dt, where V is the instantaneous voltage across the inductor, L is the inductance in Henry, di by dt is the instantaneous rate of current change, that is in ampere per second. The different types of inductors are shown in the figure, and also the electronic symbol for the inductor is also given. Kirchhoff's law. Kirchhoff gave two laws to solve complex electric circuits, namely Kirchhoff's current law, that is KCL, Kirchhoff's voltage law, that is KVL. These laws enable us to calculate the current flowing in various branches of a network as well as the voltages across various points of the network. First, Kirchhoff's current law, that is KCL. It states that the algebraic sum of the currents meeting at a junction in an electrical circuit is zero. That is, the current entering the node will be equal to the current leaving the node. Here, the incoming currents are taken as positive and the outgoing currents are taken as negative. That is I1 plus I2 plus I3 minus I4 minus I5 equal to 0. Kirchhoff's voltage law. It states that the algebraic sum of voltages around a closed path at any instant of time is 0. Let E1 and E2 be the EMF given in the circuit, and R1 and R2 are the resistance connected in series with this EMF. And due to this resistance, there will be voltage drops V1 and V2 respectively in the resistance R1 and R2. Therefore, according to the Kirchhoff's voltage law, E1 plus V1 minus V2 minus E2 will be equal to 0. That is E1 plus V1 will be equal to V2 plus E2. Next, basic terminologies in the magnetic circuit. First one, magnetic flux. The magnetic flux is the total number of magnetic lines of force in a magnetic field, and it is denoted by the Greek letter phi, and the unit is Weber. Magnetic flux density. It is a flux per unit area at right angles to the direction of the flux. The unit is Weber per meter square or Tesla. The equation for magnetic flux density B equal to phi by A. Magnetomotive force or the MMF. It is a force which establishes the magnetic flux in a magnetic circuit. The unit is ampere turns, AT, and the equation MMF equal to N into I, where N is the number of turns and I is the current flowing in the coil. Magnetic field intensity, H. It is a magnetomotive force per unit length of the magnetic circuit. The unit is ampere turns per meter. The equation H equal to MMF, that is Ni divided by L. L is the length of the coil. Permeability. It is the ability of a material to conduct magnetic flux through it. That is, the magnetic flux density B is directly proportional to the magnetizing force H. That is, B is directly proportional to H. That is, B equal to mu H, where mu is the constant of proportionality and it is called the permeability of the magnetic material. Reluctance. It is a property of a material to oppose the magnetic flux in it. The unit is ampere turns per Weber, and the equation for the reluctance R equal to MMF divided by phi. Coming to the important section, that is Faraday's laws of electromagnetic induction. First law. It states that whenever the magnetic flux linked with a circuit changes, an EMF is induced in it. Or whenever a conductor cuts the magnetic flux, an EMF is induced in that conductor. This is the first law. Second law. It states that the magnitude of the induced EMFs equal to the rate of change of flux linkages. The induced EMF E equal to N phi 2 minus N phi 1 divided by T in Weber per second or volt. That is E equal to N into phi 2 minus phi 1 divided by T volt, where N phi 1 is the initial flux linkages, N phi 2 is the final flux linkages. Substituting the above expression in the differential form, we will be getting E equal to d by dt of n phi. That is equal to n into d phi by dt volt. Lenz's law. It states that the currents which are induced due to electromagnetic induction are in such a direction as to oppose the cause producing them. That is E equal to minus n d phi by dt. Electromagnetically induced EMF. There are two types of induced EMF. First one, statically induced EMF, and second one, dynamically induced EMF. So first we will discuss about the statically induced EMF. Statically induced EMF. When the conductor is stationary and the flux is changing, the EMF induced in the conductor is called statically induced EMF. The statically induced EMF can be further subdivided into two, that is self-induced EMF and mutually induced EMF. First one, self-induced EMF. The EMF induced in a coil due to the changes of current in the same coil is called self-induced EMF. So when a coil is carrying current, a magnetic field is established through the coil. If the current in the coil changes, then flux linking the coil also changes. Hence, by Faraday's law, an EMF will be induced in the coil. This is known as self-induced EMF. The equation will be E equal to N d phi by dt. The direction of induced EMF, that is by Lenz's law, is always such as to oppose the cause responsible for inducing the EMF, namely change of current in the coil. Next is a self-inductance. So when the current in the coil changes, an EMF is induced in it, which opposes the change of current in the coil. This property of coil is called self-inductance. That is, E is directly proportional to di by dt. Therefore, we can write E equal to L di by dt, where L is the self-inductance. There is another equation for inductance of a coil containing n turns, that is L equal to n phi by I. That is, n is the number of turns, phi is the flux, and I is the current flowing through the coil. Next is a mutually induced EMF. The EMF induced in a coil due to the changing current in the neighboring coil is called mutually induced EMF. If there are two coils, that is coil A and coil B are close to each other, then any change of current in the coil A will result in mutually induced EMF in the coil B. That is mutual inductance. The magnetic flux through coil 2 due to the current in the coil 1 is given by the equation N2 phi 21 will be equal to M21 into I1. Therefore, the induced EMF due to mutual induction is given as E equal to minus N2 d phi 21 divided by dt. That is equal to minus M21 di1 by dt. Mutual inductance. It is a property of two neighboring coils to induce voltage in one coil due to the change of current in the other is called mutual inductance M. That is, M12 will be equal to N2 phi 2 divided by I1. That is, a mutual inductance between the two coils is given by the change in flux linkages in one coil due to 1 ampere change in the current in the other coil. Coefficient of coupling. The coupling coefficient K is the measure of the magnetic coupling between the two coils. that is K equal to M divided by root of L1 L2, and K varies between 0 and 1, where M is the mutual inductance, L1 and L2 are the self-inductance of the two coils. Dynamically induced EMF. The EMF induced in a coil due to the relative motion of the conductor and the magnetic field is called dynamically induced EMF. The equation for dynamically induced EMF E equal to BLV sine theta volt, where B is the magnetic flux density, L is the length of the conductor, V is the velocity, and theta is the angle between flux and conductor position. So let us see some examples. That is, first one, a straight metal wire crosses a magnetic field of flux 4 milliweber in a time 0.4 second. Find the magnitude of the EMF induced in the wire. Therefore, the given data are phi equal to 4 milliweber, that is equal to 4 into 10 raised to minus 3 Weber. The time t equal to 0.4 second. So we need to find out the EMF. Therefore, the equation for EMF equal to d phi by dt, that is equal to 4 into 10 raised to minus 3 divided by 0.4. That is equal to 10 millivolt. So the answer is 10 millivolt. Next question. A coil of 200 turns carries a current of 0.4 ampere. If the magnetic flux of 4 milliweber is linked with the coil, find the inductance of the coil. So the number of turns N is given as 200, phi equal to 4 milliweber, that is equal to 4 into 10 raised to minus 3 Weber, and the current is given as 0.4 ampere. So we need to find out the inductance L. The equation for L in terms of number of turns, flux and current is given as L equal to N phi by I. Then by substituting the values for N, phi and the current I, we will be getting the answer as L equal to 2 Henry. Okay, thank you.